In today's lesson, we're going to be looking specifically at equilibria when I'm trying to dissolve something into a solution. And those particular equilibrium constants are called KSPs, which are solubility product constants. We've discussed before that if I have interactions between solute particles, I've got interactions between my solvent particles, and then I also have interactions between my solute and my solvent particles. If my solute particle interactions are exceedingly strong, there is going to be very limited dissolving that takes place. We also learned in the previous chapter that dissolving is temperature dependent. And so that's why anytime we talk about a KSP value, it's only going to be valid for one specific temperature. We are able to find KSP values in reference resources for lots and lots and lots of different ionic solids. And so all of those constants are listed at a very specific temperature. The other thing that has to be true for a solubility product to be valid is that the solution has to be saturated. So if I look at calcium carbonate as an example, if I take that and try to dissolve it in solution, calcium carbonate does not like to dissolve in water. It will dissolve a very, very, very little bit, but not a whole lot. When it dissolves, I end up with calcium ions and carbonate ions, okay? In order for the KSP to be relevant, I have to have as much dissolved as will possibly dissolve. In other words, the solution has to be saturated in order for the KSP to be valid. Now, how am I going to write the equilibrium expression for this particular reaction? Well, KSP is equal to the concentration of the calcium ions times the concentration of the carbonate ions. Now, why did I not use this? Why didn't I put the calcium carbonate in there? Well, the reason for that, if you will recall, is that I never include solids or liquids in my equilibrium constant expressions, okay? You can't really have a concentration of a solid. Concentration is how much solution or how much solute you've got per amount of solvent. And so because this is in solution, I can measure the concentration of. When we talk about gases, we can measure the concentration of gases because they're dissolved in air, but I can't measure the concentration of a solid or of a pure liquid, either one. So that's why they're not included, okay? Notice that we don't have any coefficients, so there aren't any powers up here. So this is simply the equilibrium constant expression for the dissolving of calcium carbonate. Now, the KSP, if I look it up in the literature and I find it for calcium carbonate at a specific temperature, and I believe it's 25 degrees Celsius, it's going to be 2.8 times 10 to the minus 9th. When you look up these things in these tables, you're not going to find any units on them. And in fact, we don't have to worry about units. It's going to depend an awful lot on what kind of coefficients you have up here as to what units these are actually in. And honestly, we just simplify things and we don't worry about it. I know that the author of your book often tends to say, chemists have this propensity to make everything as complicated as possible. And honestly, that really annoys me because I totally do not agree with him when he says that. And this is an example of that. If we really wanted to make things complicated, then we would always make sure we put the units on KSP, and we don't do that. We don't put the units on there because it just isn't that important that we have them on there. All right, so once I know the KSP, and again, this is something that's given to you in a table. It's a reference value. The KSPs for lots and lots of different solids have been determined. I can then determine the concentration of the ions. Well, how am I going to do that? When this dissociates, as for every calcium carbonate that breaks apart, you're going to get one calcium ion and one carbonate ion. So that means if I would call this X, then I would also have X of those. And so the concentration of calcium ions is X. The concentration of carbonate ions is X. Well, what's X times X? It's X squared. So I'm going to have 2.8 times 10 to the minus 9th equals X squared. And then all I have to do is take the square root of both sides, and X is going to be equal to let's see here, 5.3 times 10 to the minus fifth. Now, if you were in algebra, your teacher would probably mark you off if you didn't have a plus or minus sign out here. But I don't want a plus or minus sign on this because it doesn't make any sense to have a negative concentration of something. That's not possible. So the only answer I'm interested in is the positive one. And so you don't need to put a plus or minus in front of that, regardless of what your algebra teacher would tell you, because we're dealing with a real world situation here and a negative root doesn't make any sense. Okay. So what that then tells me is that my calcium ion concentration, which is also going to be equal to my carbonate ion concentration, it's going to be equal to 5.3 times 10 to the minus fifth molar. Okay? When I express this concentration, I'm now going to make sure I put units after it because that is going to be in molarity. All right? Now, it gets a little trickier if you have things dissolving that have exponents or have coefficients in front of the reaction. So let's do an example like that so you can see that. I am actually going to do the second part of example 6.4. That's the harder part of the example. Once I do that one, I think you'll be able to go back and look at the first part of 6.4 and it will make sense. And the example I just did on the board is exactly like example 6.3. So let's look at the second part of example 6.4. And it tells us that the solubility product of cadmium phosphate at 25 degrees Celsius is 2.53 times 10 to the minus 33. Again, it's tiny, 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 so not much of it dissolves. Want to know what the concentration of each ion is in a saturated solution of cadmium phosphate. All right, so cadmium phosphate is going to look like this. Solid. Okay, so I've got cadmium phosphate, and I need to write an equation for how that is going to dissociate. So I'm going to have 3 cadmium ions, each of which have a positive 2 charge on them. And then I'm going to have 2 phosphate ions, each of which have a minus 3 charge on them. Okay, both of these guys are going to be aqueous because they are dissolving. And so again, remember that the KSP value that you have only works once this solution is saturated. And because the KSP is so small, it's not going to take very long. All right, so your KSP, they give us 2.53 times 10 to the minus 33. KSP equals 2.53 times 10 to the minus 33. Now, what's the expression look like? Well, again, I'm not using this because that's solid. So it's the cadmium ion concentration cubed, because there are 3 of them, times the phosphate ion concentration, which is squared because there are 2 of those. Okay, so there's my expression. Now, here's where you have to be careful, because once this dissociates, if I have 1 mole of this that dissociates, how many moles of cadmium ions am I going to get? You should know the answer to that. Okay, so if 1 mole of this dissociates, this is going to make 3 moles of this. Well, I don't know exactly how much is going to dissociate, but it's going to be 3 times X. Okay, how many moles of this? If I have 1 mole of this, how many moles of that are there going to be? Well, there's going to be 2. And so it's going to be 2 times whatever that X is. However much dissociated, it's going to be, I'm going to have 2 times that and 3 times that for the X amount of this that dissociated, okay? Before I just had X's, but now because I've got coefficients, I have a 3X and I have a 2X. So now I need to go and I need to plug those in here. So I'm going to have 2.53 times 10 to the minus 33 equals, the cadmium is 3X, and I have to take 3X and I have to cube it. I'm going to put 2x in for the phosphate, and the 2x then I'm going to have to take that and square it. Okay? Now, once I do that, that's going to give me this. 2.53 times 10 to the minus 33 equals 27x cubed times 4x squared. Okay? 2.53 times 10 to the minus 33 equals, I'm going to multiply those two together. That's going to give me 108 times x to the 5th. Okay, you're going to divide both sides by 108, and then you're going to have to take the 5th root. Now again, you're going to have to make sure you know how to do that on your calculator. On my calculator, what I need to do, there's a y to the x button if I want to raise something to a power. So if I want to take the root of that, I have to use the inverse or second function and then hit that button. So work with your calculator and make sure you know how to take a cube root or a 4th root or a 5th root in order to be able to solve these problems. When I solve that, I end up getting 1.19 times 10 to the minus 7th. Okay? Now, if I want to know the cadmium ion concentration, this is X, but the cadmium ion concentration is 3 times that. So the cadmium ion concentration equals 3 times 1.19 times 10 to the minus 7th, which gives me 3.57 times 10 to the minus 7th molar. Same thing with my phosphate ions. My phosphate ions, I have to take 2 times whatever X was. Okay, because this was 2x up here from that coefficient, remember? Okay, so then when I multiply that out, I'm going to get 2.38 times 10 to the minus 7th molar. All right, so that was the more complicated of the two examples. The first part of example 6.4, again, done the same way, but we didn't have quite as many exponents we had to deal with, okay? Now, I also want you to be aware that you can take these problems and you can do the reverse of them. So I want to show you an example like that as well. So we'll get rid of this so we got some room to work. All right, this time I'm going to start with a saturated zinc hydroxide solution. So I have zinc hydroxide, which looks like this. And when it goes into solution, I'm going to have zinc ions and hydroxide ions. Like that, okay? If I know that the zinc ion concentration is 1.4 times 10 to the minus 6th molar, what's the KSP? I can go back and I can flip it the other direction, okay? I can figure that out. So how would I go about working that problem where I want to solve for KSP? Again, you're going to have to keep in mind that when this breaks up, if I have X of these, I have 2X of those. I have twice as many hydroxide ions as I do zinc ions. So we've got to keep that in mind as we're going through this process. The expression for KSP for the zinc hydroxide is the concentration of the zinc times the concentration of the hydroxide squared. Remember, because that coefficient's there, so it's got to be here as a power. All right? So let's start plugging things in here. My KSP, I know the zinc ion concentration because I was given that one. 1.4 times 10 to the minus 6th. What's the hydroxide ion concentration? Well, I know the zinc, but there's twice as many hydroxide ion concentrations. So what that tells me is I have to take 2 times 1.4 times 10 to the minus 6th. And then once I get that number, then I'm going to have to square that and multiply it times this one. Okay, now don't make a silly mistake here and say, oh, I'll just take this and cube it and multiply it by 2. You can't do that because I have to take 2 times this and then square it before I multiply by this. So make sure that you're keeping your parentheses on all your brackets and stuff straight so you don't end up making a silly mistake. Okay, what you should end up with when you get finished is 1.1 times 10 to the minus 17th. And like I said, we don't put units on the KSP. Okay, so what I would highly recommend that you do, take these examples, make sure that when you plug numbers into the calculator that you're getting the same thing that I got, that the author of the textbook got when he worked the problems out. Make sure you know how to operate your calculator, because if you can't use your calculator correctly, that's going to be a nightmare for you. Okay, if you need any help with that, make sure you reach out to me, and then we'll put an additional twist on this the next time I see you.